Now I want to take a look at a mathematical description of logistic regression. Okay, we've got some data here. Here's column 1, here's column 2, and here's our target column. Now note that, very importantly, the target column is all zeros and ones. In machine learning, we refer to this as a classification problem. The idea being that we're trying to classify all the data into, say, zeros and ones, like 2 groups often. Could be more groups. So how can we deal with this? Well, there are a lot of different approaches, but logistic regression takes one particular approach. It basically says, hey, can we use the idea of linear regression and make this work? Well, it's a little bit trickier because, right, if I multiply column 1 by a number and add it to another number times column 2, I'm going to end up with like a wide range of values. And I want to restrict these values to zeros and ones. So you can start to think about this graphically. You can start to think, is there some kind of a cool like function that exists that does this? Okay, let me show you what I mean here. So if I look at, say, my x and y, and let's say that this is the line y equals 0, sorry, y equals 1. We're also going to include y equals 0 here. And what I'm doing here is I'm making asymptotes. And the idea is this. Can I create a mathematical function that's stuck between 0 and 1? So if we look at like traditional linear regression, right, maybe down here, I have these points and, okay, this isn't bad. Here's a potential line of least fit. Okay, this is fine for linear regression, but the issue with logistic regression is that if you take an extreme value here, it's not going to actually be probably good for linear regression. Like say x is 1,000, you need some huge value for y. The same thing in the other direction. It's just nicer if you can actually bound it for logistic regression, okay? So by bounding it, this is what I mean. If you have really large values of x, you get like closer and closer to y equals 1, okay? It's going in that direction. Likewise, if you have like, say, really extreme values to the left, like very, say, or x is like really negative, then you want to get closer and closer to 0. Okay, and then, well, what do you do in the middle? Well, you connect them, but note that because these are asymptotes, you can't actually do it with a straight line. That will give you something like this. It's actually done more like that. It's hard to do with the arrows already present. I can try to smooth it out for you in a minute. But there is a mathematical function that does that. In fact, now that you see what I'm trying to do with the extremes, let me just see if I can get it in there a little bit better for you. Yeah, because it's designed to be a smooth curve, not a messy curve like that. Okay, so here's the sigmoid. All right. That is what it's supposed to look like. And the idea is that this would be like about 1/2. That's the number in the middle. It's symmetric to both sides. So do you see how this visual is ideal for a target column with 0 and 1? Because I can say that everything to the right side, it's greater than 1/2 on y, it's going to go into the +1 bin. And everything on the left side is going to go into the, say, 0 bin. Okay? And so how do I go from here to here? Right? That's the idea. I think, if you can see that this is a cool, like, end game, just like for linear regression, it's actually a straight line. For logistic regression, it actually is. This is called the sigmoid. And there is a mathematical function that does this beautifully. And I believe it is f of x equals 1 over 1 plus e to the negative x. You can check extreme values if you know what you're doing. Note that e is approximately 2.7, 1828, etc. And so, you can think of it like 2 for like sometimes simple computational purposes. So if you put in like a huge value, like say 10 million, well, what's 2 to the negative 10 million? That's like 0, and you get 1, the high value. Whereas if you put in like an extreme negative, then let's see if this works out right. If you put an extreme negative, this becomes, yeah, extremely like a high positive, like 1 plus 10 zillion or something. And then that's going to be 1 over that is actually 0. So I'm just trying to like give you an indicator, which is confusing if you haven't had limits or calculus, how this will work in the extremes. Okay. And if you plug in y equals 0, you do get 1/2 because e to the 0 is 1, and 1 over 1 plus 1 is 2. Okay, so it does fit the middle and the endpoints here. All right, so how to go from here to here. Note that what we did with linear regression is that we found a multiplier, and at the end we added them up to give us, basically that gives you the hyperplane, the hyperstraight line. So what we do here is actually the same idea, one little catch. You find the multiplier, and let's just pick something random to start with. Let's just try 1 of this one, 1 times this plus 1 times this. And then what you do is you put the result inside of the sigmoid. Okay? So that first number, if I pick 1 plus times 3 plus 1 times 4, I get 7, the e to the negative 7, right? And the math gets a little complicated, okay? But the point is that it's going to end up somewhere on here. And here's something else that's pretty cool about this. The simple thing to do is to look at where x is. So what we have here, we have these are positive x values. The positive x values go to 1. These are negative x values, and then negative x values actually go to 0. So if without doing the math, I can say if I'm putting in positive 7, it's going to 1, and that's not right here. So I would get an error. It would be a miss. Okay? So it's kind of cool like to think about, well, okay, so what might right numbers be? Now that you see it becomes like a negative positive game, which is actually a cool kind of way of doing it originally, to say, oh, hey, if the combination is negative, make it 0. If it's positive, make it 1. In effect, this is the mathematics behind that, right? So how could we do that here? Well, you have to look at it a little carefully. We can say that the zeros, if we want to highlight the zeros, this is the first and the last column. And if I look at the x column 1, column 2, it's not obvious to do because it's got like well, they're close by each other. You can think about like different, and this is where, again, I'll just be honest, it's challenging for human to do. I didn't design this data set with this example in mind. I actually just picked random points. Okay, so you can see, and maybe you can see a good strategy here, that for human being, like, it's tricky if you're not picking it in advance of how you should do it. But this is also, again, how it would actually work. So let's actually go through the error process and see how we can maybe adjust it. So based on the 1 and 1, this is wrong. 1 times this would be a negative. We didn't have a 0. This is wrong. This would be positive, so this one would be right. This would be positive, so this is wrong. And again, what am I doing here? I'm just like at the bottom, because I did that pretty quickly. I'm saying, hey, do 1 times, I'm just saying, is it positive or negative? Well, if I do 1 of this and 1 of this and just sum them 20, that's positive. That should be a +1, but I get negative. So I could try, 3 of them are wrong, right? So if I want to try to fix them, I could make them both negative, or I could try to make one of them negative, right? If you think back to that error, if we are like overshooting, right? Remember this? When we looked at, say, a potential like 2D error here, and if we want to get here, but we're up here, we're like positive, then we said we want to go down, right? Our values are too high. We want to make them low. We want to make them, say, more negative. So if I choose like one of these columns to be -1, and I can be a little strategic, right? I could try to look at it, and so I could just, the algorithm though is going to randomly do it. So let's just randomly do it. What if I say this is -1 now? Well, this would still be positive, so that's out. This would be positive because that becomes positive 2, so that's in. So that's better. So this is round 2. You could say this is out, but this is good. Negative, positive, this is good. And note that this one goes to 0 if you do negative and a positive. And that's really interesting because we didn't say like where does 0 go. And I actually can't recall like where it goes. It's so rare to actually get 0, but clearly you could set it so it goes either way. By default, sometimes, a model might take greater than or equal to, and it could be, plus 1. But if you multiply this by a slightly different number, right, because it's usually not going to be that precise, be like negative 1.0001, then this one becomes negative, and this is also correct. So this simple change looks good, and in fact, why don't I try making this one, say, a negative? Do you see? So maybe like I can make it a negative 2 instead of a negative 1. So do negative 2 times the first column plus 1 times the second. Well, now I get a negative 6 plus 2. That's negative. Good. Negative 2 times 2, that's positive. Negative times negative is positive. Add it, we get a positive, which is good. Negative 2 times 5 is negative 10 plus 11 is positive 1. Positive, that's good. Negative 20, now it's clearly negative, and that's good. So you can, in fact, use this to find a way to make it work.